Hi everybody, Dr. Pingle here. This is part 3 of a lecture on spatial interpolation. In this lecture, we actually get into real spatial interpolation. So it's an exciting part. So far, we've been talking about some simple gridding tools and point density tools. All of those are sort of mildly interpolation, but here we're going to be sort of talking about more conventional techniques. So with that, let's get started. Okay, so we're going to be talking about a case in GIS that comes up actually quite often, and that's the case where we need to interpolate, we need to figure out what's going on over a larger area than we have sampled. The tools that we've talked about so far, point to raster, point density, kernel density, these all work well when we have a relatively high density of points, where we think we've really more or less pinned down the phenomena that we're trying to capture. But that's often not the case. There are a lot of times when we really can't afford, for whatever reason, and we'll talk about a couple of those cases, when we really can't afford to sample as much as we would like. So how do we predict phenomena with a relatively small set of observations? So this is a common problem. A couple of examples to illustrate this. One is monitoring groundwater. So the idea is we would like to know what's going on with the groundwater in our area. Is it contaminated? Where have the contaminants gone? Is it safe to drink? What are the water levels, for instance? And to keep track of this, we can't just look directly into the groundwater everywhere. We have to take the data that we have, whether it's existing wells or maybe putting in a couple of monitoring wells. Every well that we dig has a potential for even injecting things into the water table. So we want to be a little bit careful about that. And so we want to take the small number of observations that we have and make estimates of what's going on in our watershed. A second example comes from meteorology. Up until recently, when remote sensing has started to give us a pretty good global picture of what's going on, a lot of the understanding that we had of what's going on in the atmosphere comes from individual point observations on the ground. This might be station data. Still, a lot of what we know about what goes on in the atmosphere comes from balloon launches. And so we have these individual observations, and we need to make a prediction of what's going on sort of with the wider case from that individual data. And then a third case is related to the stuff we've covered so far. Species observations are maybe few and far between. It's very difficult to get a handle of what's going on sort of species-wide. So we might have individual sightings that we can keep track of. We might even have something like radio tags on a couple of individuals. But from those few observations, we need to make guesses about what's going on as a whole. This is one of my favorite visualizations of this problem. This comes from a species distribution map of baleen whales produced by the New England Aquarium. On the left pane, something like what we've looked at so far. This is a gridded mesh of observations, what we saw, where we were when we saw it, and we try to estimate where those species are. The problem with this is that it's fairly discontinuous. And we don't really imagine that this discontinuity reflects the underlying species that we're interested in, but rather it's partly an artifact of kind of just random happenstance, where we were, where the whales were at that point in time. And so, a human looking at this would sort of probably naturally smooth this out a little bit in their head. But to someone not used to this, they might wonder, why does this particular cell have a high value? Is there something about where the whales are? The answer obviously is no. It's just kind of a luck of the draw where they happen to have been. And so what we want to do is produce sort of a smoothed output. We want to imagine that what we saw here on the left is sort of really related to probability and doesn't really capture exactly what was going on. Now, if we had observers and we had posted them at all of the centers of these grid cells and we had watched for a long enough time, then that method this method of sort of tabulating that data would probably work. But given the relatively few observations that we can make, we need to smooth that out. And so one technique of doing that is with a technique called Kriging. This is a technique that you see over here at right. Essentially what we're trying to do is we're trying to estimate what's going on at these grid cells, knowing that the inputs to this are sort of probabilistic. And so in a way, what we're looking at here is really kind of a smoothing of the data. So that's a concrete example. Let's take a look at some of the terminology here. So you may have heard of the difference between interpolation and extrapolation. Interpolation is the process of making guesses between known points. Generally, that's relatively easy to do, at least in comparison to extrapolation. Extrapolation is where you're trying to guess what's happening outside of known points. Classic example here, if I know what the stock market opened at and I know what it closed at, I can make an okay guess about what happened in the middle of the day. I might not be accurate, there's still a lot of variability there, but that's a lot easier than guessing what's going to happen to the stock market tomorrow. Interpolation is generally, there's error associated with it, but it tends to be relatively constrained depending on how orderly the input is. Extrapolation is always difficult. It's always much harder. There's a lot more uncertainty. The nearer in terms of space, or the nearer in terms of time you're trying to guess, the easier it's going to be. It's a lot easier for me, for instance, to predict what the stock market is going to be 10 minutes from now than what it is going to be 10 days from now. Autocorrelation in space and time limit or constrain the problem of extrapolation a little bit, and yet it's still much harder than interpolation. There are lots of different ways to do interpolation. That's kind of what this lecture is all about. The way in which data is interpolated can actually make a really big difference in the analysis, and so it pays to know this stuff pretty well. On the upper left-hand panel here, we're looking at a version of this problem where we've got a series of dots here. We've got sort of x and y coordinates. And if I said, what's going on at 1, you could sort of tell me what that number is. Apart from sort of not having a very good y-axis label here, that's a known point. But if I said, what's happening at 1.5, where if you had to draw a line connecting these points, how would you do it? There are a number of ways that we could do it. So let's take a look at sort of the easiest way of connecting those lines, which is probably the linear interpolation. So linear interpolation means we essentially draw a straight line from point to point as we go. This is sort of, if you've ever done a connect the dots puzzle as a kid, this is essentially the process there. If we want to make that a little bit more sophisticated, what we can try to do is fit a polynomial to these points. And so we can add a little bit of curvature if we do that. You can sort of overshoot points and undershoot points. It tends to look a lot smoother. But how we do that, and that might seem like it's a good fit, and it might be a better fit, but the actual quality of the fit isn't necessarily guaranteed to be better with a polynomial fit than a linear fit. It very much depends on the domain that you're working in. So if a human would connect to the dots kind of one of these two ways, or sort of a combination of those two ways, one way that you can do it, and is actually quite common, and maybe more common than you think, because it's a default setting on many of the spatial interpolation operations in GIS, is the nearest neighbor interpolation. The idea behind nearest neighbor is pretty simple. You just find whatever point that you knew about was the closest, and you guess that. So if I'm trying to guess the value of what the y value should be at 1.25, I just go and look and see what the value was at 1, and that's my value. If I'm at 1 7/8, I look at my closest neighbor, which is 2, and I just report the value of 2. So this is kind of a highly discontinuous way of doing it, and yet it is actually quite easy to calculate, and it has some advantages. Most of the time, nearest neighbor is a fairly bad interpolator. As you can imagine, right? You can sort of, as a human, see the discontinuities here, and so it's sort of weird to say that, you know, at 2.5 minus epsilon, the value would be close to 1, and at 2.5 plus epsilon, the value would be closer to, I don't know, 0.2. That kind of discontinuity humans don't really like. But as we'll see as we go through this stuff, that nearest neighbor interpolator, that's the way that ArcGIS Pro is kind of guessing things behind your back. And if that sounds like a bad idea, it probably is. So you should again almost always change the default settings here to something a little bit more reasonable. To get started with an example, this is an example of temperature distribution for stations across the United States. Picked someday at some point I was preparing the lecture. The color scheme looks something like this. We've got 22.8 is kind of the high temperature at one of these stations in southern Texas, and then this kind of whitish value is at the top of the bar. Just below that is this purple. You kind of, if you squint, probably see North Dakota with that low value there. Imagine, and in fact, these are station data pulled up from some data at some point. And you can start to say, well, okay, if we know that this is the station data for the United States, what estimates could we make about places that aren't at these points, right? As a human, you can say, well, if I'm at this area in Mississippi, you know, I might, if I had to pick a color, you know, it would probably be greenish with maybe just starting to turn a little bit blue, right? And you could make a quantitative. If instead of dots here we had numbers, you could make a pretty good guess about what you think that number should be. Maybe that would make a nice addition to the slide. The first approach to figuring out what those station values could be might be using this nearest neighbor interpolator. So nearest neighbor is sort of an easy-ish to understand kind of way to do it. The way in which you calculate this might seem a little bit arcane, but it happens all the time. Again, this is a default interpolator in ArcGIS Pro and was in desktop. So it pays to know how this stuff works. The way that it's going to work is it's going to apply what's called a Voronoi polygon, which is essentially a type of point to polygon conversion. What we're going to be doing is sort of drawing the nearest neighborhood around each point. What neighborhood is defined in such a way that the point that the area of the polygon kind of corresponds to the closest point. If you imagine that these were like grocery stores and you had to walk to the closest grocery store, the polygon would tell you which grocery store you should walk to. So this is an example of a couple of points here scattered out in a space. Again, what we're trying to do here is we're trying to describe the region of influence for a group of points. So if I put a dot down and I'm here, my closest point is going to be this one, right? And I know that because the polygon that's around it tells me that that's the neighborhood of that point. And if I'm here, my closest point. If I'm there, my closest point is this one. If I'm here, my closest point is this one, and so on. If I'm here, my closest point is there. In the GIS world, these have alternative names. Another way to refer to these is Thiessen Polygons, named after an American meteorologist. Outside of geography, Voronoi is a much more common term. If you sort of look at these things from a mathematical point of view, Voronoi described these things in 1908, while Thiessen published in 1911. It's not that Thiessen is, you know, an intellectual thief or anything. He probably just sort of generated the same idea at around the same time, which happens not so uncommonly in science and math. This is kind of a fun visualization of the United States based on Voronoi polygons. The idea here is if you take the state capitals, you can draw Voronoi polygons or Thiessen polygons around them, and you can sort of see how they compare to state borders, which is just kind of an interesting way to see, how they correspond. Of course, they certainly wouldn't be expected to correspond perfectly, but for instance, California and Nevada are divided up in a pretty interesting way. It's a little more conventional, I think, on the East Coast. Gets a little bit weirder, I think, on the West Coast. There are lots of these, sort of a popular kind of a map for GIS people to generate. This is another one that kind of comes across my social media feed now and then. These are the Voronoi polygons that correspond to the closest national park. So if I am anywhere within this polygon, my closest national park is Hot Springs. If I'm here, anywhere in this polygon, my closest national park is Wind Cave, and so on. Thiessen polygons are pretty easy to make. There's a tool specifically for this job in the Analysis Toolbox. All you really have to do is put in the input points for that, and it will spit out for you the Voronoi polygons that correspond to it. By default, and you can kind of pick up on this from this example from our temperature station data, by default, you can see that it's applied to a rectangular region. So this is a conically projected view of the United States with these station data, and you can see that there's a latitude and longitude bounding box applied to this problem. You can clip that subsequently to, say, your boundary of the continental lower 48 to kind of produce a more interesting visualization. But most of the time, this comes out okay. This is an example of how that dissolving might take place. So this is taking that initial data and then applying a clip to it. So this is a dissolved layer of the lower 48. And as you can see, this looks quite a bit better and more pleasing. So it's an easy second step to subsequently process that. This is a visualization in ArcScene. And what we're looking at here is those station data, the Voronoi polygons around them, and then the height and the color of the Voronoi polygons correspond to the initial station data. And in this way, you can start to sort of get an idea of if we had to draw a surface, a raster, or a continuous surface of temperature over the United States, as we imagine that there could be. This is kind of one. Again, discontinuous, right? Because it's a nearest neighbor interpolation, but a nice approximation of that surface at the first go. This is a set of bus stops generated from Overpass Turbo. So one thing that we could do is we could take these as our initial data points, and we could ask what is the closest bus stop to me based on where I live. And we can use Voronoi polygons to quickly visually solve that problem. If we do that, that looks like this. So we can start to see what that looks like. Some interesting sort of structure to this. We get sort of polygon-ish looking things here, but we get these really interesting long strips on some parts as you kind of go down these linear tracks of the buses. This is an example of applying similar sort of analysis to supermarkets. So these are supermarkets downloaded in the Chicago area, applying Voronoi polygons to those. You might do this to sort of make a projection about what your customer base would be. You can get a sense of who's in your service area by this, right? You could do something like a buffer that would do that. But if people mostly go to the grocery store that they're closest to, which is sort of true, there's some caveats to that, but that's kind of true. You can get a good approximation of what your customer base is this way. There's a raster version of this tool, and that's called a Euclidean Allocation Tool. What this is going to do is it's going to generate a raster where the cells of that raster essentially correspond to the closest polygon. That looks like this. So this is essentially just a rasterized version. So rather than sort of creating the polygons and then rasterizing that, you can sort of take a shortcut by directly going to the Euclidean Allocation Tool. This is actually related to the Euclidean Distance Tool, which produces a raster of the distance to the closest point. In this case, this is a visualization of the distance to the nearest station observation. So if I had to sort of take a hike to my nearest station, your location on this raster would tell you how far in distance it would take to get there. This is one of my favorite visualizations that I've just seen recently of this kind of problem. This is a really fun data set produced by NASA that shows the distance to the nearest coast. And it's essentially that Euclidean distance tool applied to the linear the linear shoreline file, or a polygon file, the same. And so it's kind of a fun way to do it. The visualization comes from Joshua Stevens. The data itself comes from NASA, and the link is here below. And kind of a fun thing here. He's labeled the continental pole of inaccessibility, the point on land that's farthest from any shoreline, and similarly Point Nemo, great name. That is the furthest oceanic point from land. So don't get shipwrecked at or near Point Nemo. This would be an example of using Euclidean distance to show walk length from every point to the closest bus stop. Again, sort of a common example of this. Not only what is my nearest bus stop, but how many miles or feet or meters does it take to get there. Nearest neighbor interpolation then is essentially the process by which you assign a value to each pixel of the closest point. In effect, what we're doing here is we're creating Thiessen polygons, and then we're giving that section of the raster the value of the closest point. What we're looking at here is actually an interesting special case of inverse distance weighting, where we're really only considering the nearest point. If we extend this out a little bit, we get this kind of more broad technique, often used, but actually also not a very good interpolator, the inverse distance weighting technique. So we'll take a close look at that next. So inverse distance weighting, or IDW, is the process by which, again, we're trying to guess the value of a point based on nearby observations. If nearest neighbor makes my guess according to what the nearest observation is, IDW takes into account all of the neighbors within a certain distance, or all of the k neighbors where k is specified by the user. Both of these techniques work fairly well. So if you kind of look at the example in the upper right, if I'm at the yellow point and I say, consider, I assign me the value of the, for instance, average of all of the points within a certain distance, I would get what you see here. Now, IDW actually functions a little bit differently. It's not usually a simple moving average, although it can be. What we usually do is we weight the points value in determining an average by how close it is. So even if we're considering all of the points within, say, 25 feet, we still want to say, if I've got an observation that's 5 feet away from me, I want you to weight that more heavily than another one that's 10 feet away from me and another one that's 24 feet ahead of me. So the inverse part of IDW means that the weight is proportional to the inverse of the distance. In other words, if I'm right at my, if I'm at a distance 0 from my observations, then it's a full weight. But the weight of that observation decreases as I get further away. If I'm 2 units away, then maybe I want to give it a weight of 1/2. If I'm 3 units away, maybe I want to give it a weight of 1/3. If I'm 10 units away, maybe I give it a weight of 1/10. That would be a pretty simple way of weighting those. And as we'll see, things can get a little bit more complicated. So usually what we do is we weight these things in a way that looks like this. So if we wanted to assign the weight based on just the numerical value of the distance, we might assign, we might say, you know, if I'm 1 unit away, it has an observation of 1. If I'm 2 units away, 1/2, and so on. But I might want to change how quickly that diminishes. And so what I can do is apply an exponent to the distance. So in this case, if I apply an exponent of 2, so here w equals 1 over d to the p, if p is equal to 2, as is often the case, then if I'm at a distance of 1, then I have a weight of 1, so that's the same. But if I'm at a distance of 2, then it's 1 over 2 to the second, and I have a weight of 1/4. If I'm 10 units away, then I'm 1 over 10 to the 2, so it's 1 over 100, so I have a much smaller weight. So as you increase the value of that exponent, you apply the steepness or the rapidity with which the weight diminishes and increases. So the power value for here is often 2, and the idea here is it's something like a gravity model. The gravitational pull between two masses is related to the proportionally is related to their masses, but also the square of the distance between them. And so inverse distance weighting often uses an exponent of 2, but this is manually settable. So when we look at the tools, you can actually set that p number to whatever you want. You can set it to 3, you can set it to 4, you can set it to 100 if you want to. Not only that, you can actually set it to values below 1. So you could have an exponent of 0.5, you can have an exponent of 0.1, you can even have an exponent of 0. Now, the idea behind this is that you want to pick a value, you want to pick an exponent that reflects how things drop off with distance. And you might rightly ask, how in the world would I know that? And the answer is you probably won't. You're probably going to have to make an assumption based on the data. But you can actually generate optimal values in a really interesting way, which is that if you take the known points that you have, you can sort of iteratively take one away, or sort of pretend that that wasn't in the original data set. Try to estimate the value of that with inverse distance weighting according to a number of different exponents, so p, the p parameter here, and you can see which p parameter gave you the best fit. And if you do that for all of the points in your data set, you can generate what's called an optimal value, sort of an empirically tested value of what your data, how your data diminishes. And this is a nice way to do it. It's sort of empirically based, not done very often for whatever reason, but probably the best way to use IDW if you're going to use it at all. So as we said, the inverse distance weighting technique is essentially related to the gravity model, where the interaction between two objects is inversely proportional to the square of their distance from each other. The gravity model actually comes up a lot in geography. It's a kind of classic way of explaining distance decay, or how things become less related as they get further and further apart. So again, because this bears repeating, the weight of the observation is a value that's generated proportional to the distance, and an exponent or power value is used to control how much the weight of that observation degrades with distance. So the idea here goes something like this. If I'm at a red point here, and I'm trying to guess my value from that of my neighbors, and let's say that I've got 3 neighbors that are sort of nearby me. The one on the upper right has a value of 2, the one at the lower right has a value of 2, and the one kind of to the upper left has a value of 3. If I'm at the red dot and those are the neighbors that are nearby, what is my value? So take a minute, pause the video if you need to, and just think about that. what number would you give that red point if you were trying to guess? So one number that you might guess is 2. So the closest number to me is 2, so maybe I'm a 2. But you can see that if you sort of imagine that a 3 is nearby, you might hedge that bet and say, well, I think 2, I might be somewhere between 2 and 3, maybe closer to 2 than to 3. Maybe my value is like 2.1, 2.2, something like that. So these 3 points we could define as sort of being the 3 closest points to me, or we could say I'm considering all points within a distance of 5 as my neighbors. And so this would be a distance of 1. These concentric circles represent a distance of 1, distance of 2, distance of 3, distance of 4, distance of 5. And so all of these points are within 5 of me. This point is 1, 2, 3 units away. This unit is 1, 2, 3, 4 units away. And this one is 1, 2, 3, 4, 5 units away from me. So this observation is the closest, followed by that one, followed by that one. Observation 2 is 3 away, observation 2 is 4 away, observation of 3 is 5 away. If I were trying to guess my value, I could plug this into my formula for IDW and it would look something like this. The estimated value is going to be equal to the sum of the observation times the weight plus 1 divided by the sum of all the weights. And in practice, that looks something like this. I have a value of 2, that's 3 units away, so that's here. I have a value of 2, that's 4 units away, so that's here. And I have a value of 3, that's 5 units away, so that's here. So I add these together, 2 over 3, 2 over 4, 3 over 5. And I multiply that by essentially their distance. So this is 3 units away, so it's 1 over 3. This is 4 units away, so it's 1 over 4. This is 5 units away, so it's 1 over 5. And if I do that math, I get something that looks like this. 2.26 would be my value, again, based on a power of 1. This is a spreadsheet that sort of can calculate these things out. So you can kind of put these values in here and you can play around with a power value here. I'll post this spreadsheet up. So feel free to use the spreadsheet to try it out. And what you're going to be doing is sort of changing how changing this power value affects your estimate. If my power value is 1, what does that do to my estimate? IDW can be found in the Spatial Analyst Toolbox under Interpolation. You can specify cell size, search radius, maximum size, and power. A higher power results in less influence from distant points. As I weight that observation by the power of 2 or power of 3, those observations start mattering less. So take that example of I've got a point and it's 10 units away. With an exponent of 1, the observation, the weight of that observation is 1 over 10. But with an exponent of 2, the observation of that is 1 over 10 to the power of 2, or 1 over 100. So you can see that the weight of the observation starts to drop off pretty quickly as you start to apply exponents greater than 1. Other things that you have to apply here are a cell size of the output, a search radius, a maximum distance. These are sort of ways of applying or defining what your neighborhood is. When we do IDW, we don't consider all of the points to be our neighbors. We don't include all of those in our calculation. We only include the ones that are near to us. As you add points to an inverse distance weighting interpolation, it will smooth the interpolated surface. So this is an IDW with 1 point, which is essentially the nearest neighbor. I'm gonna, if my closest weather station is here and I'm somewhere off in the corner, my observation is going to be essentially an average of the one closest points. So you can kind of see that that generates just sort of an identical value. So that's why nearest neighbor is essentially a special case of IDW. But another way, a more common way to do this would be, I want my value to be essentially a weighted average of the 3 closest points. And when you choose 3 points, you can start to see this starts to be a much less broken up surface than the one on the left, right? That there are discontinuities, you can certainly pick them out by eye, but they're not nearly as great as the ones on the left. There's really no limit on the number of points that you would use in an IDW. You could use all of the points if you wanted to, although that's not very commonly done. This on the left again is an example of IDW with 3 points. Again, as you add points, you tend to smooth the surface out a little bit more. So the surface at right is a little bit less broken up. Again, it can still have some artifacts, and it definitely does. But in general, it's a lot smoother looking than the one at the left. This is an example of sort of seeing how changing the distance parameter or how the distance exponent affects the weights. So if we use 1, we get something that looks like the green line. If we see if we set that exponent to 0.5 or the square root, it doesn't diminish quite as quickly. But even in an exponent of 2, the influence of these points is almost nothing by the time you get out to 20 units. Whereas if you used an exponent of 0.5, at a distance of 20, those points still have some contribution to make. But the general idea is that as the power value gets higher, the distant points have less influence because that denominator is essentially going to get bigger very quickly. So by that token, higher power values tend to result in smoother surfaces. Essentially, you're reducing the impact of sort of local variation a little bit. You're smoothing things out. It's sort of more of like a moving average. As you get to an exponent of 0, then the distance effectively drops off linearly. As I said, when you're using IDW, the big sticking point tends to be that you don't really know what that exponent should be. The default is 2, again, because it sort of relates to the gravity model. It makes some intuitive sense. And those defaults tend to do an okay job. But kind of a nice way to do that is to sort of empirically make an estimate based on the numbers that you have. And so you can optimize the result or the estimated result of your interpolation by running the sort of empirical analysis first before you have to run it on the data that you don't know about. So this is where you're iteratively sort of taking out a known point, using that to sort of try out exponents to see how well they do. And then when you've worked with all of your known data, then you have a pretty good guess as to what that exponent should be based on the data that you have. This is sometimes called auto-tuning. So rather than having the user supply a parameter, the system generates an optimized parameter. I would say within the last few years, that's one of the really big improvements in ArcGIS is the number of sort of optimized or auto-tuning tools that will try to guess these parameters for you that it used to ask you to supply. And so a number of these things, hotspot analysis, for instance, now has an optimized hotspot analysis tool, and that makes your life as the user a lot easier because you don't have to guess, and neither do you have to just accept the defaults. So if natural neighbor is one of my least favorite, or sorry, if nearest neighbor is one of my least favorite interpolators, and IDW is a close second, what kind of interpolators does Dr. Pingle like? Well, this is probably my favorite one to use kind of in a conventional toolkit. This is the natural neighbor interpolation. This is a really fun one. The idea here is you look at the Voronoi polygons for all of the known points. You take the point that you're trying to guess the value at, and you put that in there. You sort of recalculate what a Voronoi neighborhood would be based on that. And then the area that's in common, the area of overlap between sort of my new point and each of my surrounding observations tells me how much I should weight that observation. So all of the weights will sum to 1. So we're just looking at sort of a percentage of weight that gets allocated to each point. And so if I'm trying to guess the value that you see here, the one immediately to my left would get a weight of 0.21 because there's a fair bit of overlap. The one kind of to my south would get a value of 0.325. That one has a lot of overlap, but the one kind of to the southwest only has a very small overlap of 0.02. So that observation would not be very heavily weighted in trying to guess my value kind of in the center of that bluish purple blob there. It turns out that this is a very elegant solution to one of the big problems with IDW, which is how, so we talked about the sort of auto-tuning of a power value, but a second problem with IDW is that how big should you set your neighborhood? What distance should that band be? How many neighbors should how many observations should I consider my neighbors? Is it 12? Is it 15? Is it anything within 100 meters? As you start to make this more complex, the length of time that it takes to auto-tune gets greater. The harder it is to guess reasonably good values, and sort of the more quickly that interpolation goes off the rails. And so Natural Neighbor really quite nicely sidesteps that problem by defining a neighborhood empirically based on the observations that are around me. Again, it weights those empirically. It's quite a clever solution. And so if you're looking for a recommendation for an out-of-the-box interpolator, Natural Neighbor is one of my top recommendations for you. This makes your life a lot easier, and I would encourage you strongly to use that as your first stop in your GIS careers moving forward. Again, the idea here is that the observation's weight is proportional to the overlap between that pixel's neighborhood and its adjacent polygons. This is a lot more effective than just using a simple radius or closest k neighbors. And again, my number one top choice for an interpolator. Interestingly, because of some really clever optimizations on the algorithm side, Natural Neighbor, although it may sound a little bit more complicated than IDW, actually runs quite quickly, which is a consideration for these kinds of problems. Accuracy is one important element, and certainly the most important element. But the time it takes to do the calculation is not completely irrelevant. And so it is nice to know that Natural Neighbor runs fairly quickly. Another good choice for an interpolator is the spline interpolation. So that is using essentially a nearest neighbor fit, but essentially the distance and the values themselves are used to make the judgment. It's a good close second in terms of an interpolator, and you'll get a chance to try these out in your notebooks. The idea behind a spline goes something like this. The idea is that if my known points are these dots here, 1 through 6, essentially what I really want to try to do when I'm guessing the values is to fit a function locally. And so I don't try to figure out what's going on with the whole pattern. I just try to sort of name a pattern that I think fits between what's going on between 0, 1, and 2. And then I separately try to figure out the pattern of what I think is going on between 1, 2, and 3. And again, I separately try to figure out what's going on between 2, 3, and 4. So that's what's known as a piecewise fit or a spline fit. It's quite effective because it's again sort of empirically driven. We're not making guesses about what's going on in our data set as a whole. We're really just trying to figure out what's going on fairly locally. There are a number of parameters that control the length and rigidity of the splines. So essentially, we can choose between our spline types. We can set a weight if we wish. You'll get a chance to sort of play around with those to see what they do. In these cases, although I'm usually pretty strenuous about encouraging you not to play with the defaults. In this case, the defaults for spline fits tend to work fairly well, and so that's why this is one of my top choices. Because you're driving this off of the points themselves rather than sort of a preconception of what everything should do, like you're doing with IDW. It tends to work fairly well out of the box, so requires a little bit less customization. So geographers tend to prefer a technique called Kriging. Kriging is a kind of spatial interpolator that essentially applies a Bayesian kind of a logic. We're trying to, again, obviously because it's an interpolator, we're trying to estimate what's going on in between these points. But instead of trying to fit a mathematical function, essentially we're trying to apply statistical logic to figure out what's going on in between these points. In the red, so this is a kind of a one-dimensional example here. In the red, we've got the results from Kriging, an attempt to connect those dots. And in blue, we have a spline fit, the interpolator that we just looked at before this one. In some places, those are fairly close. When the known points are fairly close together, as they are here, both pieces of information, or both techniques are going to give you similar results. But where the fit is a little bit more dynamic, you can start to get some fairly big differences. So in between these 2 points, for instance, a linear fit would be something that connected the lines like this. Maybe I should use a different color here. A linear fit would be something like that. A spline fit would be the blue one. And again, the nice thing about Kriging is it sort of functions sort of like a middle ground between these. It tends not to be quite as extreme as a spline fit, but it also tends to be not quite as weirdly rigid and discontinuous as a conventional linear fit. There are several tools available in ArcGIS to do this. One of these is the Kriging tool. The Kriging tool requires a lot of settings. This is probably one of the areas where the default settings I would not totally trust. They're likely to be okay, but there's a lot of sort of geostatistics that goes around in the background here, understanding what are these different kinds of Kriging methods, what are semivariogram models, there's a lot going on here. What's my sill, what's my lag, what's my nugget? You probably have not been exposed to that stuff before unless you've taken a spatial statistics class, and that's totally fine. But let's give you a little bit of an idea of what those terms mean, partly because they're really nicely illustrative of more general techniques within geography. So here we're just sort of saying you really should know how these work. So here we go. We're gonna learn how these work. So the first bit of technical jargon here is the semivariogram. The semivariogram is an attempt to model the autocorrelation of what you're looking at. And autocorrelation is a very fancy term for essentially the first law of geography, which is that everything is related to everything else, but near things are more related than distant things. The idea here is that nearby observations tend to be more similar to each other than they are to distant observations. As you get further and further away, as 2 points become further and further away from each other, they're more likely to be dissimilar. So if you think about how that plays out with, say, temperature, the temperature where I'm standing right now, if I move away 10 feet, that temperature is likely to be very similar to the place I'm at now. If I walk outside, that's likely to be similar. But if I walk to Roanoke, it's going to start to get a little more dissimilar. If I walk to Richmond, it's going to get even more dissimilar. And at a certain point, it's so dissimilar that it's not likely to be useful to helping me. It's not likely to be related to me pretty much at all, right? So when I get further away, it doesn't really matter whether I'm using the temperature in Rio de Janeiro or Munich to guess what my temperature is. Both of those are likely to be pretty far off. Maybe Munich's a little bit better because at least it's in the same hemisphere. But distance-wise, Munich or Tokyo probably just as bad as each other in predicting my temperature. So essentially what we have here is we have a function that is going to tell me how this dissimilarity occurs in practice. So it's one thing to understand sort of conceptually. As I get further away, things are going to get more dissimilar. But I can actually measure that. And so if on the x-axis I plot the distance away from me, so if I'm at the station in Des Moines, on all the other stations I have a distance away from me, that would be the x-axis. And y is going to be, and I'm going to gloss over this a little bit here, is going to be the dissimilarity with distance. So the idea here is I want to measure how different I am from that observation. And you could sort of imagine this as just sort of the absolute value of the difference. That's not exactly what it is, but that's pretty similar. You know, the greater the value, the greater the difference between the two temperatures, the more the dissimilarity. So if I'm in Chicago and I want to figure out how dissimilar these things are from me, if I go out to I don't know, Naperland, which is maybe 30 miles away, that temperature is going to be pretty similar to me. If I go out a little bit further to DeKalb, it's going to be even more dissimilar. By the time I get to Des Moines, it's going to be fairly dissimilar. And if I get all the way to LA, it's going to be quite dissimilar. And so as you plot the distance, things start to generally get more and more dissimilar as you go. But again, at some point, that amount of dissimilarity flatlines. At some point, you get so far away that none of the observations make any difference. If I go out another 10 feet or another 10 miles or another 100 miles or another 1,000 miles, they're all dissimilar and it doesn't matter, right? By the time I get too far out, these observations just really don't have anything to do with each other. That place at which the dissimilarity essentially maxes out is what we call the sill. So that's the maximum amount of dissimilarity that we see within our system. The point at which that happens, the distance at which that happens, is called the range. So that's the point at which we reach sort of maximum dissimilarity. So this is the idea behind a semivariogram. It's a way to empirically estimate how much dissimilarity there is in a system, how empirically it drops off as you get further and further away, and sort of what the maximum point of that dissimilarity is. There's also one other bit here, and that's what's called the nugget. And the nugget is the amount of dissimilarity that's going to be no matter how far apart we are. So if you think about people, the people that are closest to you in your life, maybe they're your roommates, maybe they're your family, no matter how close they are to you, you're probably closer, you're probably more like your family, and you're probably more like your friends than you are with people that live 100 miles away from you, 1,000 miles away from you. But even the people that you live with are a little bit dissimilar from you. Even if I'm at my house and I go from one room to the next room, maybe that room just is 2 degrees colder. Maybe that window has a leak. Maybe I just walked into the walk-in freezer. There's always some amount of dissimilarity in the system. And that sort of base amount of dissimilarity is called the nugget. So one of the interesting things about Kriging is that it's an interpolation that's not guaranteed to pass through the original points. This tends to be an important consideration and reflects sort of the understanding of what those points represent. If the observation that you made at that point is sort of a real concrete thing, then you want the interpolated surface to pass through those points. So a good example is meteorological station data. If I record the temperature at my station at 75 degrees Fahrenheit, that's the actual temperature. Kriging takes a different point of view, and this is again sort of imagining the point as sort of probabilistic. It's an observation, but if I came back, if I sort of took another test, I could very easily get a different result. Thinking back to something like the baleen whale distribution, if I cite a baleen whale there, yes, it's true that I saw a baleen whale, but that doesn't necessarily mean that's sort of a permanent state of affairs. If I go back 2 minutes later, would I see a baleen whale there, is kind of the idea. And contrast that with something like, if I go back out or take a different thermometer, and I take the temperature, am I likely to get the same or a different result? Now, you can drill into that theoretically a little bit and say that, well, fundamentally, maybe there isn't any difference between those two things. That's a very hard Bayesian line. But I think, but generally speaking, we're imagining sort of Kriging is sort of representing observations that have some inherent uncertainty in them, and that as a result, we don't want to treat those things as if they're gospel, let's say, but just sort of an example of what might or probably is there, but not a thing that's sort of definitely there. And that's why the surfaces don't pass through the original points. We're imagining that there's some wiggle room here, that what we saw could go a little bit in either direction, whereas other spatial interpolators will require, not everyone, but many other ones will require that the surface pass exactly through those initial points. The result of that is that Kriging tends to produce fairly smooth models. If you look at this interpolated Kriged surface based on the station data that we've been looking at so far in the lecture, you can see that you know, it's quite a bit smoother than the other types that we've looked at so far. If you look at the color of the blue dots, those no longer exactly match the surface underneath, indicating that the surfaces don't precisely go through the values. Again, that can kind of be a good thing, or it can kind of be a bad thing. It really kind of depends on what you're measuring. For temperature, it's probably inappropriate, right? Because the temperature, like we said, is sort of a real thing we've actually observed. And what we probably should do is come up with a model that is both smooth and passes through those points. But again, if these were something like species distributions, then we would want to treat this fairly differently. Another note about Kriging is that this technique is fairly computationally expensive. So that means when you're running this thing, it can take quite a long time. If you're doing this with a handful of points, and by handful I mean hundreds, then it really doesn't make any difference. But if you're dealing with millions of points or tens of millions of points, then Kriging is probably not going to be a good technique for you. When would I ever interpolate 10 million points? A LiDAR data set is a good example of this. So when I run if I scan an area with LiDAR and I use an algorithm to figure out what the ground surface is, some ground filtering algorithms or some DTM algorithms will try to use Kriging as a method by which to estimate the ground surface. Why would you do that? Well, there are holes in the data set. So if I've identified many of the points as, let's say, a building, and I remove that building, I need to interpolate or fill in the holes in between those. And when I do that, I've got to pick a way, and Kriging would be one possible way to do that. But Kriging is probably not a great way to do that, partly because it is so expensive. If I've got these tens of millions of points, I don't want to just. It's going to be computationally expensive for me to use all of those points to fill in a few holes, and there are better techniques to do that. It's still interpolation, but probably not a great use of Kriging. Why might you want to use Kriging? Well, one reason is that you might think that a ground return is a ground return, but actually a classifier that uses LiDAR won't necessarily be 100% accurate. So there is some wiggle room again. What I call a point isn't necessarily a point. And as a result, for that reason, Kriging would be attractive if it weren't so computationally expensive. So when would you use this? You'd use this when you're trying to generalize a raster from relatively few data points. And again, by relatively few, I mean hundreds or thousands. If you get into the millions, you're probably going to want to look at something else. Kriging, though, is generally considered the de facto gold standard for spatial interpolation if done correctly, and that's kind of an important caveat. We'll look at some of the newer tools in ArcGIS Pro in the notebooks that make this a little bit easier to do for sort of non-spatial statistics specialists. But you know, again, if you've got a relatively few observations, then Kriging is a really good first stop. I would probably recommend this and Natural Neighbor as the two most applicable spatial interpolators. We can look at a couple of other kinds of spatial interpolation. One is regression. Essentially, what we're going to be trying to do is predict a model based on our points and guess kind of what's going on in between them, just like we do with every other kind of spatial interpolator. Whereas Kriging is sort of a hyper-local fit. Regression is sort of the opposite, and splining is kind of something in the middle. Regression is sort of the opposite. What we're trying to do is fit sort of a trend line to it with absolutely no sense that this is going to try to go through all of the points. If we look at the points in the image, in the images that we see here, if we wanted to try to identify the pattern of what's going on with these points, we would put sort of like a best fit line like we do on the left, or even maybe a curved best fit line like you see on the right. What we wouldn't do is just sort of connect these dots in order from left to right, because that would produce this sort of jagged pattern, right, that we don't think is a real representation of whatever it is we're trying to model. That's just noise that might be due to some other factor, but we don't want to include that in our model. So think of regression as sort of really a model where we're intentionally disregarding a lot of the local variability and in favor of trying to fit a more generalized surface to gain. Often it's not for prediction, it's to gain sort of a better understanding of how the system functions as a whole. To do this, you use what's called the trend tool. So the trend tool interpolates a model surface that does not necessarily and even usually pass through the original data. Now you could make a claim that sort of would say Kriging doesn't even usually pass through the original data, but the trend tool is going to produce things that definitely don't come anywhere near passing through the original data, whereas Kriging sort of at least tries to capture some of that local variability. And you'll see why you might be kind of wondering, why would we ever do that? Again, the idea here is to get a general understanding of the system, not necessarily to just predict values. And that holds true for a lot of statistical analysis too, by the way. And we'll look at how that compares to approaches like machine learning that are sort of hyper-focused on prediction at the expense of sort of a wider, more general understanding of the system as a whole. Like a lot of other polynomial interpolation techniques, you can specify the order of the polynomial. So the order of the polynomial essentially corresponds to how many terms go in here. If you think about sort of a common algebraic expression, y equals mx plus b, that's a very low polynomial order. That's a polynomial order of 1. If we want to try to increase that, you can have y equals x squared. If you might think back to your quadratic equation days from algebra, y equals x squared plus x plus b. That's a second order polynomial, and then it kind of goes on from there. So you have to sort of decide whether your system is linear, in which case like straight line linear, in which case you've got a polynomial order of 1, or curvilinear or beyond. Let's make this a little bit more concrete by looking at an example. If I have these points, so just for a second, just look at the black dots here. If I've got these black dots and I want to make a fit of those and predict a value, essentially fit a trend line to these points, I can do that. I can do that in a number of ways, but we're going to do that in 3 different ways right here. The first way that I can capture that fit is by essentially just taking the mean of the y value. So here we've got a graph that's sort of showing the percent taking versus the 2004 verbal score on, I assume, the SATs. So one way of summarizing this, or sort of fitting a model to this, is saying is just to figure out the average. So you just add up all of the y coordinates here, and you spit out an average, and that average is something like, call it 535. Maybe it's on the screen here, and looks like not. So we'll call it 535. That's actually a 0 polynomial fit. All we are doing is saying y equals, again, thinking back to your old point slope equation from algebra, y equals mx plus b. If m is the slope and b is the constant, all we have here is a constant, right? if I try to say, given the percent taking, can you calculate the 2004 verbal? If percent taking is 0.2, what's the 2004 verbal? And if you don't have an x term in there, if you don't have any variable on the right side of that equation, all you have is a constant, and all you do is say 535. What about if percent taking is 0.5? 535. What about 0.8? 535. All we have here is a constant. We don't have an x term at all, and so that's essentially just a mean. Taking that one step further, you can say we could apply sort of a best fit line, right? This would be sort of a standard correlation coefficient or a regression. Y equals mx plus b. We can figure out the slope and we can figure out the intercept. The intercept is, call it 575. And then as percent taking increases, you sort of decrease that by a certain amount. And so a classic regression would try to fit that line. But we can add extra terms into that, right? We can say, well, that green line doesn't really capture the behavior of this system very well. What we want is a curvilinear system. And so we can add a second term in here, y equals ax squared plus bx plus c, and we get a line. If we fit the data and try to minimize the variance off of that line, we would get the blue line, right? So that's the second order polynomial trying to capture the behavior of this system, and it looks like this. We've got a different intercept. It curves off. It kind of levels off. Does this capture the data a little bit better? Probably, and we can measure that when we talk about regression. You can measure how well it does that by the R-squared value. So these are three different ways of doing it. They're all models. They all have value. That just taking the mean of a bunch of numbers is not such a bad way of doing it. Sort of like any other kind of mean, the batting average or whatever, the average male height or average female height or whatever. That has value, but oftentimes you're going to want to model things a little bit more in a more sophisticated way than that. Okay, back to geography. So that what we saw just there is sort of a classic kind of a algebra, simple statistics problem. How do we apply this to the trend tool in ArcGIS Pro? Again, what we're trying to do here is if in 2 dimensions we're trying to fit a best fit line, what we're trying to do is fit a best fit plane, or more accurately, a best fit surface. A first order polynomial will try to fit a sort of a rigid plane to the data and to try to predict temperature, try to match this plane. If you again imagine these things as heights, what we're trying to do is fit a plane that matches those points. What does that plane look like if we do the fit? Well, it's higher on the bottom in the south than it is on the top, but it's tilted towards the upper right. The west coast of the United States tend to be a little bit warmer than the east coast of the United States, at least at those high latitudes, kind of Portland versus New York or Boston. Boston is colder, and so the plane that we fit is tilted towards or down in the northeast. So we could summarize this as temperature decreases with increasing latitude, but northwestern high latitudes are warmer than northeastern high latitudes. Again, we're not so much after a rigid prediction as we are to finding an overall pattern in the data and communicating that. We can add polynomials to this very easily. So if we're using the trends tool, we just change that polynomial value from 1 to 2, in which case we're not fitting a rigid plane. We're fitting, it's still a surface, but that surface can have a curve in it, just like y equals x squared has a curve in it. So we curve this surface, and we would get a result that looks something like this. It lets us be a little bit more nuanced about the pattern that we're trying to describe. So think back to the slide from 2 slides ago where we're showing a best fit line. Does a straight line capture that, or do we need to curve that line? So here we're curving the space, and the resulting fit could be summarized maybe something like this: temperature decreases with increasing latitude. Northwestern high latitudes are warmer than northeastern high latitudes, and the interior is colder than the coasts. So we add a little bit of extra understanding to the system as a whole by doing this that has a good deal of value. So as we increase the polynomial value, we increase the explanatory power of what we're doing. Finally, as we kind of near the end of this lecture, we didn't really talk much about the dangers of extrapolating, and so rather than show it via a geographical example, I thought I would show it to you via an XKCD cartoon that I think accurately summarizes the problem. Once you get outside of your data set, you really have very little confidence as to what's going on out there. So any of the methods that you're using here in GIS or otherwise are going to be very likely to give you pretty bad results. Always be careful about extrapolating from very small data sets, but even with big data sets, you can run into trouble. So if I can kind of give you some takeaways from this, some interpolation guidelines. First of all, choose the simplest model that tells your story well. So what you want to try to do is not necessarily always predict. Maybe you want to find a trend surface that explains your data rather than sort of fits a local model. If prediction is your game, then you're probably more likely to want to use something like Kriging, which is sort of the top of the line predictor. Whatever you do, try to keep things simple. The more complicated your models get, the more likely they are to generate behavior that you're not familiar with. Ideally, you want to choose a model that matches the behavior of the system if possible. If you think back to the second order polynomial fit of the SAT data, and feel free to kind of rewind the video and take a good look at that, you'll see that the behavior of that system actually starts to increase at the very end. So that curve drops off quickly, but then it kind of hooks back up again. This is actually fairly common when you choose a mathematical model that doesn't necessarily really correspond to the thing that you're modeling. You get these sort of unexpected things. It probably fits your data for a while, but then you get some really weird things that happen on the end. So if you can choose a model that matches the behavior of the system, that's all the better. Interpolation is generally a speed accuracy trade-off. The more accurate methods tend to be a little bit slower. That's not always the case. Kriging does take probably the longest of any of the ones that we've talked about today. But even natural neighbors performs very well and is fairly fast. But in general, nearest neighbor is faster to calculate than natural neighbor. And so there is this trade-off. Think about whether it's important that the interpolated surface passes through the original points, and that's probably the most important one. You need to consider whether the observations that you're looking at are sort of true, hard. It's really important that we regard those things as exactly correct. We want to be able to definitely get those values back out of our surface if we run these kinds of tools. Or do we imagine that there's some error, that there's some uncertainty, that there's some probability associated with what we just saw or what our data represents? And in which case it's not so important that a resulting surface passes through those points. You'll get a chance to play with a lot of these tools in the notebooks that accompany the lecture. Please try to pay close attention to kind of what goes on with the output. Interpolation is probably, spatial interpolation is one of the things that I probably care about a lot more than other people. And I sort of consistently see people making bad decisions about how they're handling those interpolators. My advice is to sort of stay away from IDW. There are much better alternatives out there, and yet it's used all the time. Natural neighbor is a really strong one that's very easy to use. Kriging is another one, and the new tools that in ArcGIS Pro that sort of facilitate Kriging without all of the settings. There's some sort of optimized or automated Kriging techniques in there that will just be far and away much better than anything you could produce with IDW. Don't discount the trend tool if what you're trying to do is sort of gain an overall understanding of the system. The trend tool also comes in quite handy. So with that, we'll wrap things up. I hope you enjoyed the lecture, and we will see you next time.